In this video, we are going to learn a new carbon nucleophile. These are called organometallic reagents. All that means is that you have an organic part and a metallic part. So it has this carbon metal bond. And these are super useful in synthesis. And the key with these is that you can make new carbon bonds with sp2 or sp3 carbons. Now, currently, all we know is how to make a new carbon-carbon bond using an sp carbon, and that was when we talked about that alkyne for like SN2 or reactions with epoxides. So the neat thing about organometallic reagents is that we can make that new carbon bond using an sp or sp3 hybridized carbon. Okay. So we have organolithiums and Grignard reagents, and they behave fairly similarly, okay? So let's first look at organolithium reagents, and let's go ahead and learn how to make one. So you're going to take alkyl halides, so alkyl chloride, alkyl bromide, and alkyl iodide. And the way that you can make these into the organolithium species is you add lithium metal. And you typically have this little not symbol that means that it's straight up lithium metal. It is not charged. It doesn't have an anion or doesn't have an associated anion with it. So lithium metal. And then we use diethyl ether. This is a great solvent for any time you have carbon nucleophiles that you're making because it doesn't interact with it. What you end up getting is you've just simply replaced your halogen with lithium. Okay, so that's nominally what's happening here. Let's go ahead and make a Grignard reagent, and then we'll kind of talk about what this carbon metal bond really is doing here. Same thing for Grignard reagents. You can take alkyl halides, and you're going to use magnesium metal. So you put a little not symbol there. Sometimes you also see it with just saying magnesium without the not symbol, but I typically include that. Now, the reason I'm writing each of these out is because you get a little bit different reagent for each one. So essentially, we are making a new carbon metal bond, so magnesium. And this magnesium is actually a +2. So you're going to have your halogen hanging out there beside the magnesium. Now we write these as if they are covalent, but they are really more ionic. And that comes into play in how they react. So this is a little outside the scope of the course, but I want to highlight this if you are interested. We went from a magnesium 0, and we actually have a magnesium 2. That's why we have to have both the chlorine or the halogen and our carbon nucleophile, a carbon group here on the magnesium. This is called an oxidative addition when you insert a metal into a bond. So you are oxidizing your metal and you are adding it. So it's called an oxidative addition. Outside of the scope of the course, but if you're interested, Google oxidative addition and you will find some cool stuff. But what does affect you in this class is which one to choose. So I'm going to put a red star beside the alkyl bromide. And this is probably why this is one of my favorite leaving groups. It's also the best for making Grignards. So let's just list this here on the right side. So alkyl chlorides. So we're just looking at this guy here, the X, meaning the chloride, bromide, or iodide. So chlorine, bromine, iodine. So this is the cheapest reagent compared to bromides and iodides. Iodides are the most expensive. Now, you're writing things on a piece of paper. You don't have to do them in the lab and purchase the chemicals, so that doesn't matter quite as much, right? However, alkyl chlorides are slower to do the insertion. So when you're going from the X here to our Grignard, mgx. This would be the slowest, okay? This would be the fastest. This is like the story about Goldilocks and the Three Bears. It's like the alkyl bromide is like just right. So not too cheap, not too expensive, not too slow to react, not too fast. So it's perfect. So this is a nice balance of cost and reactivity. Can you use any of them? Yes, you can. Just typically you'd have to heat the alkyl chloride one to get the Grignard. So I want to make a note, a special note here in what all of the organometallic reagents I've written here, the lithium and the Grignard reagents, what they really look like. And we're going to draw a box here. This is a very important box. This is what I want you to think about every time that you see one of these compounds, whether it's an organolithium or a Grignard, BrCl or iodide there. I'm going to draw something of what this really looks like when it's doing reactivity. I like to think of them as these carbanions, and then it has either lithium or it has that mgx. Let's write mgx over here, actually. You'll notice here that we made a carbanion. X is equal to. So this is a carbanion. This is our carbon nucleophile. Now you don't write it like this, but this is what we are. This is our thought process, okay? So you can rationalize this reactivity by thinking about really thinking about the electronegativities. So if we think about the electronegativity of carbon, it's like 2.5, whereas for lithium and magnesium, it's much, much, much lower. Electronegativity of lithium is around 1, so 0.98. And then the electronegativity for magnesium is 1.31. And so this helps me at least fundamentally understand why the carbon is holding more of the electrons here. So anytime that you see this bond, I like to just kind of in my head, I just break that bond and I say, cool, here's my negative charge, here's my positive charge. The reason I do that is because then I can easily count how many carbons I have present to add to whatever I'm trying to attack. It's really easy to look at these reagents and think, oh, I have 4 carbons, but don't forget that's just a bond to lithium. Okay, let's do a reaction here with an epoxide. So let's first make a Grignard. We're going to use our alkyl bromide. We're going to use magnesium, the presence of a solvent. This is just our solvent, diethyl ether. So we now have our Grignard. I'm going to do an oxidative addition. I'm just going to insert that magnesium. So think about adding magnesium, break the bond, plop it right in between the carbon and the bromine. And then what we're going to do is we're going to add an epoxide. We know epoxides can react in SN2 reactions. So SN2 reactions. And then when we're thinking about this, remember that we're thinking about this carbon nucleophile. And so this is a great nucleophile for SN2, but it can also act as a base. So we do have to be careful. Let's draw our arrows here. You're going to start the arrows between the carbon-magnesium bond. You're going to attack the carbon of the epoxide, and it springs open. All right, so let's count out our carbons just to make sure we know how many carbons to draw here. We've got 3 carbons here, and then 4, 5. So we've added 2 carbons here to this 3 carbon chain. So there's 1, 2, 3, and then we have 4, and then 5. And on 5, we have an O minus. We have an alkoxide that was formed. Now we're going to check our work. 1, 2, 3, 4, 5. Cool. All right, so this is what we form from this, this first step. Now, when we have the epoxide, I also like to use diethyl ether. It's a great solvent for any chemistry where we have carbon nucleophiles. Notice here, this is very similar to our recent video. We have an alkoxide. That means we have to do a workup step, H3O+. So now we're going to protonate our alcohol to our alcohol. I'm going to make a special note here. This only works for very, very few epoxides. So I just taught you something, and now I'm telling you that, well, there's more that we have to do to this Grignard or this organolithium species. So Grignards or organolithium species, those RLI compounds that we saw on the previous slide, they react cleanly with very few epoxides. They're really wily kind of nucleophiles. They will attack, they're so strong. We need to attenuate their strength a little bit. And it works well for if you just have a simple epoxide where there's just 2 carbons. But when you start getting into anything else, they don't react very cleanly. You end up getting, get like tar and stuff in your reaction. It's not good. Instead of using Grignards or organolithium species for epoxides, it's best to use something called a cuprate. We can form cuprates from Grignards and from organolithium species. There is a lot of research done on cuprates, and there are some very specific ones. I'm going to show you one from an organolithium species here, and this is the one that we're going to be using in our class. It will give you all of the reactivity that you need. First, we're going to make our organolithium species that we talked about here. And what we're going to do is we're going to add in copper cyanide. This is one of the cuprates that we can form. So if I add in CuCN, so copper cyanide, we're going to need 2 equivalents of this organolithium species, and then you will end up getting your cuprate. So your cuprate here is going to have 2 equivalents of your R group. So we have those 2 equivalents of the alkyl group. Okay, it also is bound to cyanide, and then there's a lithium ion here. So the copper here is negative. And what happens is this still looks like, if we want to think about our thought process of what this looks like, it's still a carbon nucleophile. So you still want to think about this being this like negative charge here, okay? And then you would have this copper here. So this bond here, this is where that carbon is negative, right here. It's going to act as a carbon nucleophile. This is just our thought process, but we don't write them like this. It has a little bit more of a covalent bond compared to the magnesium and the lithium species that we're looking at. But cuprates, let's write a note here. These are well-behaved carbon nucleophiles. And this is what we'll be using for epoxides because they give us really dependable chemistry. So let's do a reaction with this cuprate that we just formed. So we're going to take our organolithium, and we're gonna make it. I'm gonna show you how to make it in like a synthesis kind of thing. So we have our organolithium, we have our epoxide. Let's do an optically active epoxide. We're just going to add copper cyanide to our solution. And then we have diethyl ether. You typically would add this in a specific order. For this class, we're just going to run the reactions like this. When you do something in the lab, just know that you would always look up a research article on the specific compound you're trying to make to figure out exactly how someone did it. And then now let's draw our product from here. So we've got the 3 carbons from our organolithium species. The copper cyanide turned it into a well-behaved nucleophile so it can react with the epoxide that we were looking at. We have our alkoxide that was formed, and then we have our optically active alkoxide that we have here. Notice we made an alkoxide. This is a carbon nucleophile. We do need that acidic workup step. So this is that acidic workup step. We're going to shake this reaction with some weakly acidic solution so that way we can protonate our alkoxide. Now on an exam, you would need to show the arrows for this, so let's just practice that out. H3O plus. We would take our arrow starting at the electrons of this oxygen and pick up this acidic proton, and there you have it. This reaction does give you this optically active alcohol, and it works well. Now, one of the things you might be tempted to do is memorize what happens with stereochemistry with epoxides and when you attack and what happens to a chiral center. And I want to show you what can happen if you try to memorize. So let's take this epoxide here. We're going to have an optically active epoxide. We're going to react it with a cuprate. We're going to have our copper cyanide and our solvent, which is that diethyl ether. And then the second step, we're going to do our acidic workup because we know we want to protonate that alkoxide. Our starting epoxide here, if we look at our chiral center, which is right here, it's the only carbon center that has 4 different things attached to it. If we label the priority, we see, okay, number 4 is back, that hydrogen. I draw an arrow. It's going to the right, 1 to 2 to 3. Cool, I have an R stereo center. Now, we know we're going to do an SN2 reaction at the least substituted position. So we're going to do an SN2 here. So we typically think we are going to be inverting that stereo center. You do invert it. We are going to invert it. So we're going to have our 3 carbons that we've added to our epoxide. This side didn't change, although it doesn't matter much because it has 2 methyls. And this side, that methyl, it's still coming forward. It just got pushed up. This center did get inverted. However, let's go ahead and label the label R and S for this. Oh, I'm going to do my second step. Sorry, this step number 2, we protonated it. Bam. Okay. So if I'm labeling R and S here, this side here would be 1, 2, 3. My proton is back. That's 4. Oh crap. I still have R. This stereo center is still R. We did invert it though, because that methyl is now going up. So this stereo center is R. Let's just confirm and let's just do a reaction that we have done before where we've seen that stereo center. Switch. Let's kind of start to understand what's happening here. Let's do another reaction with an epoxide using an alkoxide here as our nucleophile. So when we do this reaction, again, we don't need that second workup step because this is our proton source. Okay, The product from this reaction is going to have our alkoxide that was added to our epoxide. Try to say that 3 times fast. Alkoxide that was added to the epoxide. Alkoxide that was. I need to sleep more. Okay. So let's do R and S for this. Okay, easy. This one here is R because it's the same compound as the one above. We do have an optically active starting material. Let's look at the chiral center we made on the right. Here is our chiral center. There's 4 different things attached to it. Our proton here is going back. Let's label 1, 2, 3, 4 on this. So the oxygen is the highest atomic number, so this is going to be 1. If I look next, this side here would be 2 because it has that oxygen later on down the chain. 3 would be the methyl, and 4 would be the proton going back. So if I use an arrow to show what's going on here, 1 to 2 to 3, I have an S stereocenter. So we went from R to S. So it did it. It inverted. Exactly what we were thinking, because we know SN2. So that's where the SN2 happened. SN2 inverts. So what the heck happened here? We did the same thing. Our ethoxide here added on the other side. It pushed that methyl. It's still wedged, but it's up. Same thing that we did on the reaction above. And the key here is that the carbon is definitely inverted, but look at what we added. We added a carbon nucleophile. So even though we did an SN2 reaction here on top, it inverted, but the priorities of the groups changed for this bottom reaction. We've added a group that now this is number 1 priority. Almost everything we've done so far in this course, when we do SN2 reaction, you'll see R going to S because all of our nucleophiles tend to be the number 1 priority. And so that's how that ends up switching. So the key here is that in the mechanism, both invert the stereocenter. They still invert the stereocenter. However, we are adding a group that just happens to have this chiral center be the same as the starting one. So whereas in this top one, the group we added was the 2nd priority. And in the bottom one, the group we added was the 1st priority. So I think the key here is that you want to invert the stereocenter, then do R and S afterwards. And the easiest way to do the inversion is that if the group that is on that chiral center in the beginning, over here on the left on this epoxide, is coming down, you just want to keep it either wedged or dashed. In this case, it's wedged, and you just push it up, and that means that you did invert it. So the center, the chiral center is inverted. However, R remained R. So a note for yourself is you must always check the labeling of RS. So you must always check the stereocenter, even if you know it inverts. So what you add can change whether it goes from R to S, or if it remains the same. It's just a label. RS is just a label that we use to communicate. So for carbon nucleophiles, sometimes when you add them, the carbon center is inverted, but sometimes it will remain the same stereochemistry when we use our label of R or S. So you do need to check this. Let's talk about some limitations with Grignard, organolithium, and cuprate reagents. In particular, let's just look at a Grignard reagent. The conjugate pKa of this is like around 45 or 50. So this is very, very, very basic, okay? So very basic. The same holds true for all of our organometallic reagents here. And that's that anion that I was kind of talking about, that carbon anion. This is such a good base. So for organolithium, Grignards, these cannot contain any acidic protons. So you can't have like an alcohol hanging off of your Grignard or a nitrogen with a hydrogen there, any sulfur with a hydrogen. You also can't have any like alkynes hanging out with your Grignard or organolithium species. Also, stay away from any carbonyls with these. I also want to make another note about I also want to make another note. You cannot have leaving groups on the alpha or beta carbon. Let me show you what I mean here. So if you were to try to make this organolithium species with this alkyl bromide, we know this is like an anion here. What happens is that it'll just kick out your leaving group and you'll end up getting ethylene, which is a gas. So that's no good. You could even have a bad leaving group on that beta carbon and it will still kick it out. You also can't have a leaving group on the alpha position or the carbon that has the anion. This ends up making a carbene. And we haven't talked about those yet, but they're pretty cool things. And essentially, it just gives you a mess. So you'll definitely want to avoid doing that on your organometallic reagent. And one more note here about Grignards and organolithium species in particular. They do not do SN2 reactions well with alkyl halides. So if you were to have, say, this alkyl lithium plus, we'll just use this alkyl bromide, diethyl ether, you will get a mess of products. You will not get what you're trying to get, which is that new, let's see, 1, 2, 3, 4, 5, 6. I have 1, 2, 3, 4, 5, 6. See, even I still count. So you won't get this alkane. This will just give you a mess of products. You can use cuprates. Cuprates can do this. However, we typically use a Gilman reagent, and we're not learning it here. Instead, I'm going to show you the way that we're going to be mainly using for our class, which is using that alkyne. We know that these can do SN2 reactions very cleanly. Here's our carbon nucleophile. We've added 2 carbons, 1 and 2. 1, 2, 3, 4, 5, 6. Okay, and how do I get to this alkane? 1, 2, 3, 4, 5, 6. How do I get to this alkane? this is a reaction, a nice little review for us. This is that palladium on carbon, H2 palladium on carbon, that hydrogenation. So this is how a really nice, effective way to get to our alkanes that we are looking for. So avoid SN2 reactions. So avoid, we don't do it with alkyl halides. You'll end up getting a mess of a product. All right, so that's it for our organometallic video. And in this video, we also talked about how the best thing to do for epoxides is to use a cuprate. So cuprates are really useful, and they are those well-behaved carbon nucleophiles that you can get very good reactivity for and expected reactivity. All right, I will see you in the next video.